kill Martha. Why did you say that name?
It's his mother's name.
What are the odds of two men at random both having mother's name Martha? Hi, I'm Jim Kekalius. I'm a physics professor at the University of Minnesota and the author of The Physics of Superheroes. Today, we're going to look at the physics behind some DC Universe films. Must not have been too deep. Wow, that would be like about 11 meters, 30 to 40 feet up. I did a little bit of research. It turns out that there's a whole sport that is high diving into shallow pools. And the world's record is like 11.5 meters that someone jumped and fell into a pool that had only 30 centimeters, about a foot of water. If you just drop an object from, say, 11, 12 meters and ask how fast is it going when it reaches the bottom, if you would neglect air resistance, it's going about 44 meters per second, maybe 80, 90 miles per hour. But if you come in horizontal, you're maximizing air resistance. And so you're converting your gravitational potential energy into kinetic energy. But some of that energy goes into work, pushing the air out of the way because you have a large surface area. And so the amount of energy available to you as kinetic energy is reduced. So your velocity is reduced. A parachute travels much faster when it's tied up in the backpack than when it's spread out. When the parachute is spread out, it falls much slower in the backpack. So similarly, the Joker comes down the way these extreme jumpers do, horizontally, to maximize his air drag and decrease his speed. So instead of 44 meters per second, well, let's say he's coming in at 20 meters per second. Let's say it's about 45 miles per hour. The force is still quite high. It's about over 3,000 pounds to stop him in the space of about 1 meter once he hits the water. But there again, if you can stretch out the time by spreading out that force over as much of an large area as possible, the pressure is reduced. In fact, the world record for highest jump into shallowest water, 11.52 meters, height into 30 centimeters of water, was by Darren Taylor. Joker may have actually beaten that, but I give the Joker an 8 out of 10 because I want to stay on Mr. J's good side. Let's ignore issues like air drag and his source of energy that he would need to eat constantly in order to have enough caloric energy to run so fast. In the human brain, processes happen faster than we tend to experience them here. But no signal gets sent from neuron to neuron at a speed that's roughly faster than a millisecond, a thousandth of a second. The blink of an eye is 100 milliseconds. So that's still very fast compared to the processes on the time scales that we live. Let's assume that the Flash is running at a stride that he covers a meter, 3.3 feet, in a millisecond. So that's 1,000 meters per second. 1,000 meters per second is 2,250 miles per hour, which turns out to be almost exactly 3 times the speed of sound. So he could travel at Mach 3. He can't actually run on a vertical surface because in order to run, we require friction. You push backwards with your foot and the ground, because forces come in pairs, the ground pushes back on you and propels you forward. But that frictional force requires there to be some weight on the surface that you're pressing down. If the wall is completely vertical, then no part of his weight is pressing against the wall. Maybe his first step presses against the wall, but then it no longer does. If he's traveling at 2,250 miles per hour, you can ask how fast does he fall due to gravity in that time scale. And in about a millisecond, he's only fallen about 10 to the minus 6 meters, which is about the width of a red blood cell. So he could appear to be running across the wall and not fall down because the effect of gravity, but the amount that he falls is imperceptible. But again, if he's trying to go faster than the human mind can respond, then this is why if he doesn't look where he's going to trip. We speedsters have to stick together, and he gets an 8 out of 10.
Why did you say that name?
It's his mother's name.
What are the odds of two men at random both having mothers named Martha? This movie that came out just a few years ago, and each gentleman is in their 30s, then their parents were born in the 50s or 60s. How common was the name Martha back then, in the United States at least? Not that common. Martha, in the 1950s, was only the 49th most popular female name. In the 1960s, it was the 94th most popular female name. Now, of course, these characters' names were set in the comic books that go back to the 40s and the 50s. In the 1930s, Martha was the 24th most popular name in America for women. So the question is, how do we calculate this probability? If the case is given Bruce has the mother named Martha, what is the probability that Clark has a mother named Martha? Well, then the probability Bruce has a mother named Martha is 1, because we're specifying it. So it's just multiplied by the probability that Clark has a mother named Martha. So that way, if it's in the 1960s, the odds of this happening are only 0.2%. If you just say Bruce and Clark are two random individuals, what is the probability that they each have a mother named Martha? The probability goes way down. Think about a dice. You have 6 sides to a dice. What's the probability that you roll a 1? 1 out of 6, 16%. What's the probability that you roll 2 1s, snake eyes, with 2 die? Well, you need 1/6 on one times 1/6 on the other. It's 1 outcome out of 36 possible outcomes, or 2.7%. So it's much less likely if you say 2 random individuals, what's the probability that their mothers are both named Martha? If they were born in the 1930s, it's 0.005%. If it's in the 1960s, it's 0.0004%. Let's assume that they're using the names in this movie that were set in the comics that were coming back in the 1930s. Then they get a little bit of boost in probability, but not much. Still very unlikely. I would have to give this no better than a 2 out of 10. Wonder Woman. I'm not going to complain about issues of her strength or speed and reflexes. We're going to grant the character a one-time miracle exemption from the laws of nature. In the comics, it was said that Wonder Woman's bracelet was made of Amazonian metal, which is why she was able to deflect such the bullets. We can actually figure out how strong the bracelet would have to be. We look at the momentum of a bullet coming in. The bullet has a weight of maybe 20 grams, but it's going 1,000 feet per second, approximately, let's say. Deflects back, so has a momentum in and a momentum out. So there's a change of momentum of twice the initial momentum. To change the momentum requires a force applied for a given time. If we say the time of the ricochet is a millisecond, 1,000th of a second, then the force the bracelet has to supply is about 2,700 pounds. Quite high. The surface area is very low, so the pressure that the bullet exerts on the bracelet, 70,000 pounds per square inch. What kind of metal can handle that? Pretty much all of them. Cold rolled steel, stainless steel, they're all strong enough to support a compressive pressure of 75,000 pounds per square inch. I'm not going to argue with her strength, but the bracelet itself, I give this a 10 out of 10.
It's called memory cloth. Notice anything?
If you're going to dress up like Dracula to beat up criminals, you got to have a cape.
Regularly flexible, but put a current through it. Molecules realign, becomes rigid.
Shape memory fabrics, then becomes rigid. You can use it for hang gliding. Those things actually exist. We're used to phase transitions where, say, ice melts, becomes water, or water boils, goes from the liquid to the vapor phase, becomes steam. But there are other types of phase transitions that we've discovered where materials go from one crystal structure to a different crystal structure. And that's pretty much a one-way transformation. Some materials can have a reversible transformation. You can undo it by warming or some other process. It used to be that the shape memory materials were metals for the most part, like nitinol, which is used in eyeglass frames. Presumably, Wayne Technology has developed a fabric that via the application of an electric field or maybe some electric current passing through it, undergoes this phase transition and undergoes this change. There is the Wearable Technology Lab at the University of Minnesota, where they're developing materials that compress under the application, say, of a temperature that are being used to develop new suits for astronauts. Since it's Batman, I give it 8 out of 10. I'm going to say that's going to leave a mark. John Osterman is accidentally locked into a chamber that removes his intrinsic field. In the comics, it is explained that the intrinsic field are all the fundamental forces except gravity. Well, the fundamental forces of nature, there are 4: gravity, and then there's electromagnetism, the strong nuclear force, which holds the nucleus together, and the weak nuclear force that is responsible for some radioactive decays. Without electromagnetism, there's nothing to hold the atoms together. Without the strong force, there's nothing to hold the nuclei together. And so he would be actually taken apart at the very subatomic level. Once he is reborn as Dr. Manhattan, he seems to have independent control of his quantum mechanical wave function. So quantum mechanics says that every object can be described by a mathematical function called the wave function that contains all the information about the object. If he is able to access his total wave function, it has the entire history of the object is contained in it, which is why he experiences time as backwards and forwards as well. If you can have control over your wave function, there's a phenomenon called quantum mechanical tunneling that would enable you to go from one position to another instantaneously. So presumably that's what he's doing when he's teleporting. And from the wave in the term wave function, there is a wave aspect to nature which enables certain phenomena like diffraction patterns. You send light through a grating and you see a series of spots due to the fact that the light has interference through the multiple slits. You send an electron through a grating and it shows the same type of interference pattern, even though it's a particle. And that's because the wave function interacts with the slits the same way light does. Dr. Manhattan presumably is diffracting himself, and that's why we see multiple versions of him in the clip. So I'll give him an 8 out of 10.
It is forbidden. It is forbidden. It is forbidden. It is forbidden.
Superman changing the flow of time. He does this in the comics all the time by traveling faster, so fast that he breaks the time barrier. Well, how fast is he going here? We can figure that out by looking at the distance he travels and how long it takes him. And the ratio of those two is his speed. We know the radius of the Earth. It's a bit over 6,300 kilometers. So we can conclude that the radius of his orbit is a bit over 10,000 kilometers. All right, so the distance he goes in one orbit is 2 pi r. So it's 60,000 kilometers in one orbit. How long does that take? Well, we can count how long it takes him to make, say, 10 orbits. And we can conclude that his speed is about 400 to 500 million meters per second. The speed of light is 300 million meters per second. So he's going much faster than the speed of light. So he gets points for indeed violating physics and doing that. Of course, he loses points because if you're going that fast, I don't know how you're constantly changing direction. Because in order to change direction, you need some other force to be able to pull you in towards the center of your circular orbit. So he loses points for that. So I would say overall, 5 out of 10. Aquaman talks to fishes. If you give him a miracle exemption from the laws of nature to account for the power, this part is just perfectly fine. When you think there are electrical currents in your brain and they're constantly changing direction, stopping, starting, moving from one neuron to another, any change in electrical current creates an electromagnetic wave. It's the basis of radio. So you create electromagnetic waves just by you thinking right now. These are extremely weak electromagnetic waves, roughly 1 billion times weaker than the radio waves that are in the room with you right now. We never think about the fact that we're surrounded by radio waves unless we can't get a cell phone signal. Aquaman has presumably a special ability to be sensitive to these very weak electromagnetic waves when he thinks and when he's communicating with other species. Seawater is 1 million times more conductive to electric fields than regular deionized water. So he's in seawater, which is a great conductive medium for the electromagnetic waves. The fishes have a special organ to detect these electromagnetic waves. Sharks in particular, their organs are so sensitive that you take a AA battery, 1.5 volts, and you attach one wire up in, say, Boston, off in the Boston Harbor, and the other wire off the coast of Florida. And the shark would be able to detect that electric field. Extremely sensitive. Once you make the miracle exemption that he has this ability, I give Aquaman 10 out of 10. Superman's X-ray vision. We can see when light shines into our eyes, either directly from a light or reflected off of an object. Kryptonians apparently can also see by emitting light, being both the source of illumination and the detector. He can apparently emit light in both the high energy part of the spectrum, X-rays, and the low energy part of the spectrum, infrared light, heat vision. X-rays come, the wavelength of an X-ray is about the size of an atom, and it gets scattered by the electrons in an atom. The more electrons, the more the scattering. Water has 10 electrons, H2O molecule. The calcium in your bones has 20 electrons. So the bones, your skeleton, are much more effective at scattering X-rays than the rest of your tissues, which is why your skeleton shows up so starkly in an X-ray image. They say X-ray vision can't penetrate lead. And it's true. Lead has 82 electrons, which makes it a very effective scatterer of X-rays. But gold has 79 electrons. It should be just as good as scatter. So the images that we see here for Clark's X-ray vision, that I'm giving a good grade to, but it gets downgraded by being able to actually create photons of light from the eye that get reflected back and detected again. So there I'm going to have to downgrade him. I'll give him maybe 5 out of 10. Well, you don't have to be crazy to do that, but it helps. So she has some superpower that enables her to create these very high intensity sound waves. The sound waves are the same type of propulsive force in an explosion. Say, dynamite or something exploding. People get knocked down, windows break, buildings can be shattered because of the air molecules traveling so fast, slamming into an object. And it's the air molecules that are doing it. Okay. That's going to cost you some points. Here she's hanging on to the motorcycle, maintaining her balance. I don't doubt that there are skilled athletes that can actually do this. And then as she catches up with the other car and is holding on to it and then moves relative to it, well, if she's holding on to the car, she's traveling at the same speed as the car, So her relative velocity to the car is 0. Then even when she moves a little bit forward and all, that only requires her a small additional relative velocity forward to get to the front of the car. Harley Quinn maintaining perfect roller skating form during this explosion, not so good. So I give this maybe a 6 out of 10.
Your phone charged. Your phone charged.
Superpowers.
And your phone charged.
Well, you think you can?
Yep, and the phone blows up because phones are not supposed to be charged up by lightning. The batteries work by a chemical reaction. Chemical A and chemical B go to chemical C and D, and they do it in such a way that they build up electrical charges on the terminals, and then you can use those electrical charges to power your phone. And once you've used up all of the chemical A and B, you can force the reaction to run backwards and go backwards from C to D back to A and B, and that's recharging your battery. Zapping it in this way is not only not going to recharge the battery, but it's going to fry all of the microchips that you have in the phone. He's a nice boy. But I give this only a 2 out of 10. If you're going to